So the final speaker of the lightning talk session is Valerio Mariani.
So good afternoon, I'm Valerio. I'm head of data analysis in the data management group of IANA, presented this morning. I would like to tell you a little bit about LCLS-Stream. You heard about it today in Jana's talk, in Hannah's talk, and in the context of IRI. And I would like to tell you a little bit about it and where it comes from. It's not.
May not connect to my computer.
Okay. But can I change the slides menu? Yeah. Yes. So the LCLS-Stream, the LSSDA idea was born within the context of the Summit Plus project. So when Summit was decommissioned, Frontier was not ready yet. So Summit was given to academic institution essentially for free. They were invited to propose academic research project, and they could use they could get allocation, and that's exactly what we did. Now, when we process our data away from LCLS, what we usually did in the past was copy the XTC files. XTC is the format that we use internally. It's optimized for speed of writing, and we would just copy the files remotely. But XTC files need our own framework to be interpreted, to be read, and to apply all the corrections that needs to be applied to the data. So we would install our PSANA framework that you heard about remotely, and then remotely we would do data reduction, compression, and pass the data to the application. We had, aside from the fact that XTC are usually huge, especially if they contain the readout of every diode, instrument, detector for a certain beamline, there's the problem that you need to install and run the framework remotely, right? And here, Summit was, architecture was PowerPC, and at the time we were not sure that we could run our framework on PowerPC. So we said, let's try a completely different approach. Let's read the XTC file remotely. Let's run our framework locally, sorry. Let's run our framework locally, do all the calibration that we need to do locally, reduce the data, maybe just send what we are interested in, and then just send this. So the idea is that when the data leaves the facility, we call it science ready, meaning that no other information for the facility is needed to interpret this. And this is what we did. We compressed the data, more of this on the next slide, and we sent it to the application remotely, which in this case was PyTorch, because we are training the system. So the architecture of the system was more or less this. We had MPI data source is a PSANA process that reads the data as fast as possible. We had several ranks running across nodes. They would send the data to a cache, and then the consumers from the other side, from Oak Ridge, would pull data from the cache. The reason to use a cache in the middle was twofold. The first was to mitigate fluctuation in speed of the reading or of the consuming of the data on the Oak Ridge side. But also, we did the reading and the calibration on S3DF, so on the 4 nodes of our cluster, which are quite powerful, but don't see the internet outside, while the cache was running on a node that could see the internet outside, and so could stream the data outside. So it was also a way for us to separate the reading with high performance from the streaming from something which can safely see the internet. We prototyped and demoed this last year at the Smoky Mountain Conference, and we could transfer data to Oak Ridge with a speed of about 3.8 gigabytes per second. This is compressed data, however, and when you look at the uncompressed data, we are probably sending about 5-6 gigabytes of data. And currently, LCLS-1, so running at 120 hertz, generates data at around 1.5 gigabytes per second. So this is already enough to send the data as fast as it is generated now. Of course, this will not be enough with the high repetition rate, but in our defense, this was done with no optimization on either side. So we're sending the data through an SSH tunnel, and we hope that when everything is up properly, we can improve the speed with time according to the needs of LCLS. What did we send and how did we trigger this? So David Rogers from Oak Ridge created a REST API, which was running with a simple fast API server, which would get a simple JSON message like this, saying basically, this is the experiment that I want, this is the kind of detector that I want, and I would like to have it streamed at this address. And what we were sending was a blob of binary data with the internal structure of an HDF5 file. So we will not write the file to disk at all. We'll create it in a binary blob in memory and then send it. The reason for choosing HDF5 file is that users are very familiar with it. And so it's just a very brief, very small modification usually of code that can read the files to get the data instead from the socket and read it. And also we could use all the compression and all the different filters that are available for HDF5 files because they work the same when you create the file in memory. And that's what we did. We're not tied to HDF5 files, so the LCL streamer is pluggable, but this is what we chose, let's say, as the default. This is a complicated slide, but let me guide you through this. What we did is we started manually our streaming, and then the streaming was received on the other side. But then we started thinking, why don't we integrate it with what we already have at LCLS? You saw in the talk from Vincent before that from the ELOG, you can trigger a lot of things. He showed the graphical interface. The ELOG at the center is connected through the data movement system at the top that moves the files on the offline file system and through Kafka messages. And the same goes for the ARP, which can trigger jobs locally on S3DF or remotely, for example, at NERSC using the Super Facility API. They all subscribe to Kafka messages, and they are all aware with the ELOG at the center of what's going on. So we said we could have a user, maybe sitting at the beamline or externally, which would, through the ELOG, could trigger a request to an LCLStream API server, which would then start the streamer at the bottom left. The streamer at the same time start the cache, which we now call an GStream buffer. And that would send the data remotely, where we would trigger the job remotely to start in coordination with the streaming that starts locally. So we started developing all the pieces for this let's say, pipeline. Initially, David Rogers perfected the LCLStream API. You need to authenticate when you request an experiment because we need to know if you can access it or not. We have the mandate to protect the privacy of the data for our users. And he developed a package called Certified, which simplifies a lot. You use it to make the request to the API, and it automatically generates the certificate if you need, and it shows the API the right certificates depending on which API you connect. Then the ELOG, I mean, we worked with Wilco and Murali, who internally in our group developed the ELOG to start to integrate this. And then we have the other pieces missing, the LCLS streamer, which I told you about a few slides ago, and the NNG stream, which is itself the cache. The cache is a dumb cache. So whatever comes in, just sends it remotely and has a pushback system. So if the receiver doesn't read data fast enough, of course, the cache fills up and then stops the LCLS streamer from reading the data. And this is basically the other component, sorry, to trigger all the jobs locally and remotely is being developed by David Rogers and it's Psyche. And all these packages are a different state of development. The ELOG is almost complete. The LCLStream is almost complete. LCLStream API also, and we are trying to finish the developing of these and put it at the stage where we're putting everything together. We can run local tests with a lot of these components already working. The last few slides. So I said that we send HDF5 files, but the whole thing is pluggable. And the idea, and this answers the questions that you also had from my point of view you had before, how do we convince people to use the same standard, the same software, the same packages? I don't think we can, but we can offer them the data in the formats that they need. We started working with David, Aaron Brewster, and Nick's team with the idea of plugging into the infrastructure that they already have, where they get the data from the synchrotron, so that we stream the data from LCLS looking almost exactly with the same format, so that we can go directly in their pipeline. And we are working with them at this time to make this true. Yeah, this format from text series is very well documented and defined, and we are trying to make the data that come out of LCLS follow this. One final thing, LCLStream is actually was born to send data remotely, but my coworker Kong, who's sitting over there, said, well, the important thing here is that it separates the task of reading the data from the task of processing the data, right? And this can happen locally if the two don't look the same way. For example, the PSANA is designed to serve you single event after single event as fast as possible. That's not what you want when you have a GPU. When you have a GPU, you want maybe a block of events close together in memories that you can copy into the GPU, right? So he created a pipeline where the LCLS-streamer is running, but it's not sending data remotely. It's just sending it to a local socket, which then draws data from to feed the GPU. And in this way, he can keep everything always running at 100% without any dead time. And that's basically what I had to show you. Oh, sorry, this slide is not formatted correctly, but this is a big collaboration between us, Oak Ridge, and people at NERSC and at Berkeley National Lab. And we even convinced a person, the graphic person at SLAC, to create an image for our project. Especially, this was designed when we were sending data to Oak Ridge. So the idea is that we send data from California to Tennessee, training machine learning and model, and then the data comes back and helps in the solution of the structure. And yeah, so this is what I had to tell you. And this is the stage that the project is in. So if you have any questions for me now, or if you want to contact me, this address, I'm happy to answer.